Hello everyone, I'm Liu Shiqiang, a postdoctoral researcher from Tsinghua University, Beijing, China. My supervisor is Professor Rong. On behalf of my research group, I'm very pleased to share our latest research on stretchable sensors with you. My topic today is a multifunctional stretchable sensor able to detect fluid flow, strain, and temperature. My presentation will include three parts. First, some background information about our research. Then, the main work we have done, including the design and working principle of the sensor, its fabrication process, and some validation experiments. The last are some conclusions we have got. Nowadays, stretchable sensors have attracted lots of interest due to their deformation tolerance and compatibility with human skin. They can be conformably attached on human skin and imperceptibly monitor epidermal stimuli, such as skin temperature, strain, surface airflow, and so on. Temperature of human skin is an important physiological signal giving an indicator of physiological state. Epidermal strain, usually caused by muscle activity, allows pulse monitoring, gesture recognition, and so on. Skin surface flow induced by human motion also indicates valuable information of physical and physiological states. For example, detection of skin surface flow can get information of heat loss from human skin. Our previous research has also demonstrated that detection motion-induced surface flow can realize motion capture and motor function assessment. Although various stretchable temperature sensors or strain sensors have been reported in existing work, there are still many challenges in developing such a multifunctional stretchable sensor. For example, how to monolithically integrate temperature, strain, and flow sensing with low cross-coupling using simple structure and simple conditioning circuit. Especially, we haven't yet found a stretchable flow sensor up to now. Here, we propose a multifunctional stretchable sensor based on thermosensation, enabling multi-sensations of flow, strain, and temperature. We develop a simple and low-cost ink printing technique using homemade silver Ag-Ecoflex composite ink to fabricate thermosensitive ribbons on Ecoflex substrate to form the stretchable sensor. Low cross-coupling among multiple sensations is implemented by using the scheme of concentric annular structure design, constant temperature difference conditioning circuit, and an adaptive filter. The stretchable sensor has merits of high integration, simple fabrication, and low cost, and demonstrates promising potential in applications of wearable healthcare monitoring and human motion capture. As shown in this figure, the sensor has two concentric annular thermosensitive ribbons, the inner and the outer ones. While working, the inner ribbon is jaw-heated and is therefore called the hot ribbon. Jaw heating generates a convection heat transfer to the surrounding fluid. The fluid flow increases the convection heat transfer, which will increase the jaw power of the hot ribbon to keep constant temperature. So, the hot ribbon works as a flow sensor using jaw power as an indicator of flow velocity. The outer ribbon has negligible jaw heating due to its large resistance and thus is called the cold ribbon. It serves as an ambient temperature sensor while working. A constant temperature difference conditioning circuit, which is a so-called CDD circuit, is used to regulate the two ribbons. It maintains temperature compensation for flow sensing. It is noticed that the resistance of the two ribbons may vary with the mechanical strain. Fortunately, the concentric annular design on the two ribbons helps to make a self-compensation to strain effect. Specifically, the cold ribbon also serves as a strain sensor that compensates the strain effect on flow sensing using the hot ribbon, just like the temperature compensation. Taken together, the stretchable sensor using the hot and cold ribbons competently detects flow, temperature, and strain simultaneously. Here, the figure shows the fabrication process of the sensor, which mainly includes three steps. The first step is ink preparing. Silver flakes and Ag-Ecoflex are adopted as a filler and matrix respectively to make stretchable composite ink with good thermosetting and thermosensitive properties. The concentration of silver flakes dominates the electroconductivity and stretchability of the silver Ecoflex ribbons, which is 76% here. Methyl is a butyl ketone solvent is used as a dispersion agent here. It helps to reduce the thickness of the ink for easy printing and prevent the curing of Ecoflex at room temperature. The sensor's substrate is also prepared in advance using Ecoflex. The second step is sensor printing. Printing technique is adopted here due to its low cost in manufacturing stretchable electronics with customized designs. Here, the thermosensitive ribbons, wires, and electrodes are formed on the Ecoflex substrate at the same time. Finally, the fabricated sensor is heat treated so as to ensure the evaporation of solvent, curing of Ecoflex, and sintering of the silver flakes. Experiments are conducted to validate the sensor's effect of multi-sensations. The left graph here shows the results of temperature sensing using the cold ribbon of the sensor, where the TCR is estimated to be about 0.2% per degree. The right graph shows the strain sensing results using the cold ribbon. The resistance of the cold ribbon increases almost linearly with the applied strain, whose sensitivity is around 4. Decoupling of temperature and strain sensing is an interesting topic. A feature extraction technique may work to deal with this issue. For example, decoupling of skin temperature and human pulse, which will be conducted in our future work. Here, the graph shows the response of the hot ribbon against flow velocity, which indicates that the sensor is able to detect the flow velocity from 0 to 14 meters per second with errors less than 0.45 meters per second. To solve the strain effect on flow sensing, we propose a hybrid compensation method, including concentric annular design and a CDD feedback circuit. However, residual strain induced artifact still exists in flow sensing output, as shown in the blue curve. Here, we propose a digital adaptive filter using least mean square filtering technique to solve this issue and realize perfect strain compensation as shown in the black curve. In conclusion, we propose a multifunctional stretchable sensor that can detect the flow, temperature, and strain stimuli simultaneously. Low-cost ink printing technique using our homemade silver Ecoflex composite ink is developed to fabricate the sensor. The flow detection with temperature and strain compensation is achieved for the stretchable sensor by using the scheme of concentric annular ribbons, the CDD circuit, and a tailored design adaptive filter. Multifunction integration, simple and low-cost fabrication allow the proposed stretchable sensor being a promising wearable device in applications of health monitoring, and human motion capture. Thank you for your attention. I will be delighted to answer any question you may have. Thank you.